Hey, Topic Analyze Math and History, and we are going to be learning about finding the area under a curve. So in this video, we're going to try and find the area of an irregular shape. So, when you try and do that, this is one of the most common lessons you would find in a pre-cal or a calculus class. So basically, these are the fundamentals of calculus. So what we're gonna do is try to find the area of this shape shown right here. But hang on, we can't exactly measure out the shape because it looks like this, and it has a curve on it. It's very difficult to find the area of a shape when it has curves on it. If we try to compare with other kinds of shapes, like squares, rectangles, and circles, it's going to be different because these shapes have formulas that are fixed, like a equals base times height, that is a square, or pi r squared, that is a circle, or base times height divided by 2 is the area of a triangle. The problem is, what's the formula for this? Well, you can't really find one because it's really hard to calculate, and if you grab a ruler, it's really hard to even measure. What we could do to solve the problem is, even though we have a curved line right here and a shape right here, why don't we put in lines or rectangles to fill it in, and then we can calculate each of every rectangle and see what the sum of inside here is, the sum of the area. That makes our answer a little bit more accurate, but not 100% accurate. If we wanted to make our answer even more accurate, we have to add more rectangles and make them a lot more smaller, basically pixels in a video game. But it's still not 100% accurate because it's still curved, and you can never ever have it 100% accurate by putting in more rectangles or pixels. But, however, when we find the area of a curve in the calculus field, it will bring us to a perfect 100%. So we can use a formula that we're going to use to perfectly and accurately measure this shape right here without having to add any pixels. To a correlation and to understand this more, if you ever played Super Mario in the 1980s, Mario doesn't look like a human. He looks more like a pixel because in the 1980s, video games literally just came out. But if you look at the real world in perspective, our world is not made of pixels like Mario and Minecraft. Minecraft is made of pixels. We are not made of cubes. So, to make things more accurate and to make things more round, if you ever play Super Mario in 2020, basically, Mario looks more like a human, not a pixel. That can show us that the more pixels we add, the more accurate our answer becomes, and the more accurate the figure right here looks more rounded. If you try to ever see it transform in a way to make it more accurate, here's the last example.
1 bit, 2 bits, 4 bits, 8 bits, 16 bits, 32 bits, 64 bits,
128 bits.
But without having to add in all those bits and those pixels, we can use finding the area under a curve to get it 100%. So let's get started. To find the area under a curve of an irregular shape, there is a formula we're going to follow. The formula is the area of an irregular shape is the integral of your first boundary and your second boundary. Then you have to find the function of x, or whatever you're trying to calculate, and then find the derivative. So, we're going to explain 3 parts of the formula. What this crowbar symbol means, because it looks like a crowbar, what the function of x represents in the equation, and what the symbols dx, or the derivatives, symbolize. So let's start with the integral. So when you draw an integral, it sort of looks like a crowbar. And the reason why it is useful in calculus is because it tries to limit down your workspace, or it narrows down what you're supposed to literally be working on. When we place the numbers 1 and 4, 1 on the bottom, 4 on the top, that is saying, okay, what you are trying to calculate must be in between the points 1 and 4 on the x-axis. Here's an example. By using the symbol the integral, it's saying that here is our first boundary, do not cross the line, and here is our second boundary, do not cross the line. And you must calculate the area inside here. You can't go out of it or you'll be breaking the boundaries. So the integral is basically saying, okay, this is your workspace. Mario has to stay in between those pink laser thingies. So let's look at the second part. F of x, or the function. If you were ever in algebra and you heard the symbols f and x, that is saying it's the function of x. One that plays a role when you find the area under a curve. Not only it makes the equation more sensible, but it also describes what the line or what the slope of that thingy is. Here's an example. Not only the 1 and the 4 and the integral is trying to limit the workspace, your function is trying to work on the workspace, or trap it in. Here is x squared. Right here, this u, aka a parabola, is also limiting the workspace. It's limiting this part, which makes a curve. So when you see an equation in calculus, in this formula, it is saying what the slope or what the line is to help shape the shape in the problem. So here's the line x squared, and here's the integral 1 to 4. What is the irregular shape of the area? Or what is the area? That's why it's called the area under a curve, because you're literally finding the area under the function that makes the curve. The last part we're going to look at is the dx, or the derivative. It will make more sense to actually solve the problem and learn it as we go. Because if I explain it right now, it could be very frustrating to shout it out, and it also could be very, very confusing. So let's actually start with a problem.